So again, for all this huffing and puffing we're doing going up this hill, at the time all this was flat. You wonder, wait a minute, how did this all remain a sort of flat, relatively shallow environment? Subsidence. Most places where sediments are laid down, the weight of those sediments, the mass and gravity, will cause the region to sink isostatically. And a first order assumption a number of sedimentary rocks experts usually start with, shall I say assumed until evidence show otherwise, is that the rate of subsidence will approximately equal the rate of deposition. This is by no means a perfect assumption, but because you can't always measure subsidence rates or uplift rates immediately, if you start with 0 and then see that you're horribly wrong, you can try again and iterate from there. So we're just about the top of the hill. I also want to point out there's a second igneous unit. This is actually the oldest widespread igneous unit in San Diego County. It is the Santiago Peak Volcanics. And there we are. You can see that ridge in Del Cerro neighborhood is one of the better places within the city limits to spot Santiago Peak Volcanics. This was right around the Jurassic Cretaceous boundary. Now, there wasn't a major extinction back then. There was just things changed. But this was shallow volcanic. You can actually see lava flows. We'll get a place to look at this more intimately down the hill. But yeah, this is sort of subduction when there was volcanism right here, and it represents one of the older units. Now, one of the things you're going to want to figure out is what evidence do we use to deduce that the Santiago Peak volcanics, which have been heavily altered, are older than the granites that make up most emission trails in a good chunk of the peninsula ranges. This is one of the few places they come in contact. And we get a chance to do a number of relative dating exercises connected with that. So here we are at the summit. So I want to point out how you have these very flat-lying mesas that are about the height of the mesa we're on here. You're also going to see some mesas. There actually is a little bit of tilt here. Not surprising given how much tectonic uplift we've had here. We're, I think about 800 feet above sea level here, and roughly speaking, and yeah, sea level change does explain some of this, but a lot of it is tectonics, and generally, while tectonics can produce a fairly even rate of uplift, it's not perfect, and presently most of the rocks here dip slightly towards the ocean as the rate of uplift gets a little higher as you move inland due to the current state of things. Now, a lot of people, when they come up here, sort of think again of these canyons. I want to once again emphasize what I said in an earlier speech, that what we're looking at here, the erosion and the carving of these canyons and terraces, these mesas we're on are technically wave-cut platforms carved by the waves, back when sea level was higher and land surface was lower. That this used to be all very flat-lying stuff. The fact we're on a hill and all this is a consequence of uplift and erosion. So if you're standing here at the time, you would have seen the big river through here. But wait a minute. What about those mountains right there? Yeah. And what about them? Well, you can see, first of all, that we're also not too much far below that saddle right there, and there's several gaps in the mountains, and there's a bigger gap on the north side of Fortuna right there. So the river could have wound around those mountains. And we have some evidence that those mountains are there, have been there a lot longer. We have some radiometric dates from these mountains, from the granites and crystals within the granites. Two, you notice how the mountains tend to get a little steeper right at about the level of where these mesas are. Top out. I'll argue that these were all bases that all these were flat surfaces carved by wave action, and that the waves must have been smashing into those mountains when they were essentially islands, because we have plenty of rocks that look like these sedimentary rocks on the other sides of those mountains. And so, you can also see Mission Gorge Boulevard going up through that little pass there. That pass was probably at one point a course of the river when the entire land surface was this high, even on the other side of that gorge over there. There's also been substantial amounts of erosion and excavation of the El Cajon Valley during this time of uplift. And I'm guessing the material in there was a little softer. That would make sense. So you can actually really see these areas where the waves must have been crashing against these islands. And it's kind of neat to imagine that this at one point we would have been standing maybe chest deep in a sea here, in a shallow sea on the continental shelf, and watching waves slam against those cliffs. There might even be beaches there. I guarantee you erosion has long since removed any evidence of those. And then you can also see that as the land got eroded more, you can see those cliffs sort of change in slope below the tops of the mesas. They're a little gentler. So if you ever do rock climbing up there, that spot right ahead is a popular rock climbing spot, you are essentially climbing ancient sea cliffs, which is kind of cool. A few other things to point out. There's so much up here. So we have down in this valley we have both Santiago Peak volcanics. You can see it on that hillside that's been cut by the construction road right there. Try to get a better photo of it. And of course you have these sedimentary units. If you look across here, you can actually see a well-defined line where the grasslands give way to chaparral and brush. That, my friends, is your contact between the sedimentary units and the igneous units. The sedimentary units support clays, which give rise to grasses. The chaparral prefers the rockier soils of the volcanic rocks that don't produce as much clays, and has a competitive advantage there. So all sorts of different foods for thought. Now we're going to look for one more piece of evidence that these intrusive bodies are older than the sedimentary rocks. So we're going to show you one, an outcrop down the hill from here. Two, I'm going to show you an outcrop, a picture of an outcrop that I was at about 6.5 years ago. It's up along Route 52 as it crosses just north of Fortuna, and generally, if you're driving, you can't view it because you'll be a road hazard, but I walked along the bike path and spotted it, and it was awesome. All right. One other thought on the course of the San Diego River. What you kind of see here is an interesting sort of cross-cutting relationship, or something kind of happening. It's hard to explain. As a mountain range rises, rivers will, if a river can keep up an erosive rate, the rivers cutting through the mountain range will get steeper and steeper and erode more rapidly. So assuming the mountain range doesn't rise too rapidly, or the land surface doesn't drop too rapidly on one side of the mountain range or sea level, you can maintain a river that will basically act as a buzzsaw cutting through a mountain range. So what this kind of tells you is that the San Diego River is probably a relatively old river, especially by the standards of California. it existed before that mountain range was particularly significant. And I wish I knew if the rocks on either side were part of the same pluton. It would not surprise me if they were part of a different one. It would not surprise me if they were the same. I can see, but they do look very similar, so from this far away. But yeah, so I suspect the river cut through at a time when the entire land surface was higher, and then as sea level dropped and the land surface rose, it continued to cut through there. So what you're looking at is a classic incised meander cutting through a mountain range, or a river buzzsaw effect, as they sometimes call it more affectionately. So one of the challenges I've found is determining whether or not the Pomerado is conformable with the Mission Valley. There's a couple reasons to suggest it is not conformable with the Mission Valley. The most obvious being the erosion, the soil horizon that forms on the top of the Mission Valley, that caliche that makes everything fizz. The second is there's been several other methods of measurement have concluded the Pomerado is substantially younger than the Mission Valley by a few million years. These I'm all going to have to check when I get back to the lab. Again, you have to sort of like do as much thinking and calculating measurement as you can in the field, but also there are going to be things that only make sense once you have access to all your references. And this is why a good field expedition benefits from extensive research of existing work beforehand, so you can make the most of what is often a very limited time in the field. Now I do see some cobbles in here, but I think this is an artifact of the erosion process. You can see that the cement holding the Pomerado together weathers a lot faster than the cobbles themselves, and that these cobbles are subject to mass movement. I guarantee if you dig down just a few feet, yes, good luck digging through all these cobbles, you'll be back into like pure Mission Valley formation. And I think what's happened here is that this stuff gets kind of muddy after the rain, and these cobbles get kind of embedded by the constant traffic of hikers and mountain bikers on this stretch of the trail here. And by the time you get down about here, it's looking pretty purely. So the other thing is I don't see any obvious layering. When we had the stadium contact with the Mission Valley, even in those transition areas where there's cobbles present, the cobbles appeared layered, which suggests they're all part of like one single event. Whereas here, these cobbles do not appear any layered at all. And we see the Pomerado is very well layered. So the biggest hint is the soil horizon. Anytime you see soil happening, there is erosion and weathering. And that would also suggest that the Mission Valley Formation was above sea level at that time, because you had a soil forming there, a fairly deep soil that got all the way into top. You can also see the Mission Valley is not that thick. In fact, we're going to be seeing the bottom of it right on that ledge. All right, back.